Okay, so the trig function composition, right? You've heard like, or you've done compositions of functions before. That's where you take one function and you kind of plug it into another function, right? That's composition. And so here what we're going to be doing is kind of plugging inverse trig functions into trig functions and kind of like trying to evaluate or simplify them as best we can. So like an easy example, which is not on, well, it's in our papers there, but I'll do something otherwise. So like, for example, a basic kind of composition that's super straightforward would be something like this. Okay, where you take like the cosine of the arc cosine of root 3 over 2. Right? Since the cosine and the arc cosine are inverses, the property of inverses, right, is that they just kind of cancel each other out and they are gone. And this is just equal to the root 3 over 2. Okay. So just end up equaling our this root 3 over 2. If you don't believe me, right, we could also take it in steps. We could say, all right, well, the way we normally could evaluate this is we evaluate what's inside the parentheses and then do cosine of whatever that answer is. And so, again, for the arc cosine of root 3 over 2, okay, arc cosine of root 3 over 2, that is pi over 6. Pi over 6. Okay. But then what is the cosine of pi over 6? It's root 3 over 2. Right? And so we end up with, like we expect, right? Cosine and arc cosine cancel each other out. Just like we had sine of arc cosine, if we had tangent of arc tangent, and you know all the reciprocal trig functions too, right? Those are exact inverse of each other, so they cancel out. But then, of course, we run across other situations. For example, like this in number 118a, where we have the tangent of the arc cosine of root 2 over 2. So now we've mixed things up, right? Tangent and arc cosine, they're not exact inverses of each other. So we have to do some other kind of manipulation here, right? We have to do something else. So we can't kind of do what we did here, where we just kind of cancel them out and say it's going to be root 3 over 2. But we can kind of do something like this, right? We can evaluate what the arc cosine of root 2 over 2 is. What cosine of what gives us root 2 over 2? Pi over 4, right? So we could say this simplifies then to be just tangent of pi over 4. Okay, so evaluating the inside part first, right? Using the order of operation, right? Evaluate what's inside the parentheses there first. And then we can evaluate tangent of pi over 4, which is what? 1, right? So we get 1. Right, so again, that's not too bad. All right, that was pretty painless. Arc cosine of root 2 over 2, we could evaluate that. Tangent of that, we could then evaluate. So no problem. Okay, but then we run across in letter B, they throw this one at us. Cosine of the arcsine. So again, they're not exact inverses of one another. Of 5/13. Cosine of the arcsine of 5/13. And now we hit a bit of a snag because our previous strategy that we just used here won't quite work, right? Arc cosine of root 2 over 2, we knew that, right? Because that's part of, it's a ratio from the unit circle. But 5/13 is not a ratio that's on the unit circle, right? It's not one of those memorized ratios that we have. And so we need one more kind of strategy here to kind of help us out. So what can we do? Well, we can kind of go about it the same way we did here and the same way we did here, where we evaluated the kind of the arc cosine first, and then we take the cosine of it. So let's take a little closer look at this arc sine of 5/13. Okay. Now arc sine of 5/13, right? The output of that, the value of that, what it should equal is going to be some angle measure, right? Just like arc cosine of root 2 over 2, when you take the inverse cosine of root 2 over 2, it gives us an angle, pi over 4, right? Arc cosine of root 3 over 2 gives us pi over 6. The input of an inverse trig function, the input is a ratio, the output is an angle. So the output of this should be some angle. We don't know what it is, right? Because it's not in the unit circle. So let's just say it's some generic thing, theta. Okay, some generic angle theta. So if this statement is true, then we can also say, if we take the sine of both sides here, sine of the arcsine of 5/13 equals sine of the right side here, theta. And of course, we know that sine and arcsine, they what? Cancel out. They're gone. So we're left with 5/13 equals the sine of theta. And of course, like, okay, great. Now what though, right? What can we do? Well, again, sine, okay, right, relates an angle with the opposite side and the hypotenuse in a right triangle. So we can draw a right triangle with this given scenario, right? We can say, all right, well, this guarantees, or this says we have some right triangle here, okay, with an angle theta, where the opposite side of that angle theta is going to have a value of 5, okay, and then the hypotenuse will have a value of 13. Now, this same theta, okay, this same theta that when we take the sine of it gives us 5/13, it's this same theta right here that says theta is arcsine of 5/13, right? We just kind of like made a variable here. So in other words, I could rewrite this problem instead of cosine of the arcsine of 5/13, I could say, oh, this is just cosine of theta, right? Theta is the same thing as the arcsine of 5/13. We defined it that way. So then I can say that this is just saying cosine of theta. And so now to evaluate this, it's merely evaluating this. And so to evaluate cosine, I need the adjacent leg and the hypotenuse. So we know it's going to equal something over 13, but I need to come up with this adjacent leg. And what is that adjacent leg there? 12, right? Okay, yeah, it's a Pythagorean triple, 5, 12, 13. And of course, if you couldn't, if you didn't know that it was 12, you could do, 5 squared plus b squared equals 13 squared. You get b squared equals 144, and b then is going to be 12, right? And so, yeah, we get 12/13. So you can kind of bypass having to actually calculate or know what theta is. We can use the information we know about theta to create a triangle to then allow us to solve for the cosine. Okay? This strategy also works for this problem and this problem as well. Okay, you can do the same thing. It's just, those ones are easier. We didn't need to do it necessarily, but here in a situation like this, we had to do it. But it'll work for the other ones too. Questions on any of that? Okay, so let's just try another one here and just see. So I'll just throw another one at us here. So I'll do 120 letter A. So 120 letter A is tangent of the arc cotangent of 2. Okay. So they're not quite exact inverses, right? Tangent, arc, cotangent, arc, exact inverses there. But we can do a similar kind of thing. Arc cotangent of 2, all right, we can say is going to be equal to some angle theta. Okay, and so therefore, if I take cotangent of both sides, I'll get that 2 equals the cotangent of theta. Okay, 2 equals the cotangent of theta. Again, I just took cotangent of both sides there. And so that means then, and again, just for, well, we can stop there, or if you don't like cotangent, you could just do the reciprocal of both sides if you want to and say 1/2 equals tangent of theta, right? Either way, it's okay there. We just reciprocal both sides there. 2/1 becomes 1/2. Cotangent becomes, well, 1/10. All right, as again, we can just draw a little triangle here to help us out. Okay, a right triangle, put theta in there. Tangent is opposite over adjacent. Okay. And so let's be 1 squared plus 2 squared, so that's 5, and then square root of that will be square root of 5 then for the hypotenuse. I guess we don't really need that, but anyway. Okay. Tangent then of that arc cotangent of 2 is the same thing as evaluating just tangent of theta. Okay, tangent of theta, opposite over adjacent, 1/2. Which is just the reciprocal of the 2 there. But again, just showing you the strategy works in general. Okay, the strategy kind of works in general for you to help you kind of get your bearings and stuff like that. Okay. Question on any of that? I want to do one more at least, because there's also some negatives. Okay, so there's the idea. That's the basic strategy we're going to follow. One other little thing I want to talk about though too is like sometimes they'll throw some negatives at us too. So for example, in 122, okay, there is, let's see here, the secant of the arctangent of -3/5. Secant of the arctangent of -3/5. In the previous problems, when I went and drew those triangles, right, we had the positive values. We were taking arcsine of a positive 5/13, arc cotangent of +2, which made it nice and easy. All those triangles, if we think about, you know, in what quadrants those, or for what, you know, values of theta, for what values of theta will arc cotangent be positive and arcsine be positive, those are going to be in quadrant 1. And so we kind of are drawing these triangles essentially in quadrant 1. But now for arctangent, it's going to be a negative value. And with arctangent, again, remember the range for arctangent is -π/2 to π/2, right? So arctangent of theta, or I guess I'll say x. Arctangent of x. When you give your answer for arctangent, the answers are from -π/2 to π/2. Okay, so let's see here. Well, that's going to be a function, right? I think it's more like this. Okay, so but anyway, we're going to be in the 4th quadrant here for arctangent. So we want to draw our triangle in that way. So rather than, you know, drawing it kind of like it's in the 1st quadrant here, we can kind of draw some axes. All right. And again, since arctangent is, well, I guess I'll write out the thing here. Arctangent of -3/5 equals some theta. Take tangent of both sides. Okay, like that. Okay, and so to be in quadrant, bless you, to be in our quadrant here, I'm going to go ahead and just draw the triangle down here in the 4th quadrant. Okay, there's my theta. Kind of messy. There's theta. Okay, there's the right angle there. And then we're going to have to go opposite that is going to be 3. And since we're going down from the x-axis there, that is where our kind of -3 is. And then the 5 will be adjacent, right? Opposite, -3, and then a +5 here. Okay, +5 there. I know we're talking about the length being a negative number, but that's how we set it up there. Okay, it's got to be negative because we got to be in the 4th quadrant. Arctangent goes down this way, okay, in the 4th quadrant there. And so then we use the Pythagorean theorem to get the other sides. So 25 and 9, it's going to be 34, so the square root of 34. So that's a matter of evaluating the secant of that theta. Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse, so this will be hypotenuse then over adjacent. So root 34 over 5. And there it is. Okay. So for arctangent and arcsine, remember arctangent and arcsine, for the negatives, they go in the 4th quadrant. Okay. For arc cosine, you're going to want to draw your triangle in the second quadrant if it's negative. Arc cosine of the negative second quadrant. Okay. So both arctan of a negative and arcsine of a negative, they go to fourth quadrant. Okay, but arc cosine of a negative is in the second quadrant. Okay, just like when you evaluate arctangent of a negative, okay, your answer ends up being just in the fourth quadrant kind of, or the negative version there. It's the fourth quadrant, but you know, from the negative side, not from the clockwise direction. The clockwise direction, not the counterclockwise direction. And then arc cosine is the second quadrant. Okay. So that's the idea there. Okay. So there's a few of those. We can do another one too. Let's take a look at another one of those maybe. Yep. We have tangent of the arcsine of negative 5, 6. So we'll do one more of those here, and then we'll move on. Okay. Okay, so tangent of the arcsine of negative 5, 6. Okay, so one more here. We'll do like that. And then we'll take a look at the packet. Okay, so again, arcsine, negative 5, 6. We'll go write that over here. That's equal to some angle theta. It's going to be a theta in the fourth quadrant because we have a negative ratio here. So we're going to end up with negative 5, 6 equals sine of theta. Draw our triangle such that it's like in the fourth quadrant. Okay, you don't need to bother trying to draw this to scale. You know, you can just kind of just draw the triangle. Okay. You can see though that theta is coming clockwise. Okay. This is why when we evaluate arcsine of a negative or arctangent of a negative, we get negative angles, right? Because that angle theta is being created from the x-axis and going clockwise. Right? We go this direction, we have negative angles. All right, negative angles. All right, and so sine is opposite. So this will be negative 5 over hypotenuse of 6. And again, I know the negative has to go with this side right here because it's going down, right? Going down and the positive 6 for hypotenuse. And then Pythagorean theorem to get the rest. So it'll be 36, take away 25, so 11, so the square root of 11. And now we have that, we just evaluate tangent. Okay, so tangent is opposite over adjacent over root 11. And you can leave it like that, right? Don't have to worry about rationalizing. Okay. So that's the idea. Questions on that? Questions on that? Inverse trig is a little bit tricky when it gets to the negatives because it changes the orientation of the way we think about things. But that's the idea. All right, question on any of that? All right, so that's those, and then I think let's see here. I wanted to. Oh, I guess I should look at some of these other ones here too. Right, forgot. So like moving on down to like the next section there, from 123 to 128. I'll look at like numbers 124 here. Okay, so on number 124, I'll show you here what it looks like. All right, number 124. In the directions here, it says in exercises 123 to 128, use the figure to write the expression in algebraic form given that y equals the arc cosine of x, where 0 is less than y is less than pi over 2. Okay, so essentially you just want to simplify these things, okay, and you're going to use this diagram to help you do that, right? So let me just redraw the diagram here. So here's our little diagram. Okay, and then we have our angle. They use y instead of theta here. And then x for this leg, and then 1 for the hypotenuse. Whoops, off the screen. There we go. Okay, and then for 124, they want us to evaluate, for example, sine of y. And again, we're given y equals the arc cosine of x. Okay. So essentially, they want us to evaluate a problem that's just like the stuff that we just did, right? This is just like the stuff that we just did. If I plug the arc cosine of x in for the y right here, I'm evaluating sine of the arc cosine of x. Right? Do you see that? It's the exact same thing we're talking about. What's different? Well, now instead of arc cosine of a ratio of a number with numbers, it's just x, or the ratio x over 1. And so nothing's really changed here. It's the same kind of strategy that we're going to use. Okay, we're going to take that arc cosine of x. They already chose to set it equal to y, not theta, so we're just using y for our angle here instead of theta. We'll take the cosine of both sides. Okay. X equals cosine y. You can see where this triangle developed then, right? Y, there's our angle. Cosine is the adjacent, so x over the hypotenuse of 1, right? So this is the ratio x over 1. So there's adjacent leg over the hypotenuse, x over 1, right? So they set up the triangle for us already. Right? All we need to do now is evaluate what sine of y is going to be. Well, for sine of y, we need the opposite leg over the hypotenuse. And so we'll do Pythagorean theorem here. So we'll say, I don't know, a squared plus x squared equals 1 squared. Right? And we want to solve for that a. So I'll say a squared equals 1 minus x squared, and then square root both sides. Okay. Again, since we're in an equation setting, I should have a plus or minus in front of that square root, but because we're talking about the length of a triangle here, okay, we'll just use the positive version of it. Okay? Because we're told that it's between 0 and pi over 2, so we know our answer is all going to be in the first quadrant. It's going to be positive. So this is square root of 1 minus x squared. Okay. And so then to evaluate sine of y, it's opposite, square root of 1 minus x squared over hypotenuse 1. And boom, there it is. Okay. And now that you have that triangle, all the other problems here are going to be super easy. I mean, I'll show you here. All these are just asking for cosecant of y, secant of y, cotangent of y, tangent of y. So, I mean, you have this third side, so literally it's just using SOHCAHTOA to get the other ratios there. Super straightforward. Okay. Questions on any of those? It's going to be, that's pretty much it. Okay. And again, I'll hopefully get you some time here to work on that in class, so you'll be able to ask questions too if you come across them. And then the last section from the book that I'm going to be assigning you problems from is this right here, where it's essentially taking this and extending it. Right here, it was like one, kind of these 6 problems right here are all centered around this, and now they're just kind of changing up a little bit. You'll notice here again, all that's changed is that instead of having numbers in there, it's now got variables or expressions, stuff like that. So, I mean, I'll just pick one of these here. Let me do, I don't know. I'll do like 136 maybe. Okay, so I'll do 136 now, just to show you that one. Okay, and then we'll look at letter K. So 136 is the secant of the arcsine of x minus 1. Now we want to evaluate that. Okay. So again, we'll take this piece inside here. We'll say, all right, well, let's figure out what arcsine of x minus 1 here. That's going to equal some angle theta. Okay. Again, the input for an inverse trig, input is a ratio, the output is an angle. So it's got to equal some angle theta here. We'll take sine of both sides, and we get x minus 1 equals sine of theta. Okay, so now we can go ahead and draw that right triangle. Okay. And for all these, we're just going to assume they're in the first quadrant there. So theta is equal to, well, since sine of theta, so sine is opposite. So the opposite here is going to be x minus 1. And the hypotenuse is going to be just what? Just a 1, right? Because, again, the ratio here would be x minus 1 over 1. And then we want to evaluate the secant of that theta. Again, arcsine of x minus 1, we defined it to be equal to theta. So then evaluating secant of arcsine is the same thing as just evaluating secant of the theta. So secant is 1 over cosine. So let's see here. Cosine is adjacent over hypotenuse. Secant of theta would be hypotenuse over adjacent. So hypotenuse is equal to 1, but we need to come up with that adjacent side. And how are we going to come up with the adjacent side? Pythagorean theorem, right. So x minus 1 quantity squared plus b squared equals 1 squared. Okay. And it's up to you whether you want to, square out the x minus 1 quantity squared. I think, actually, I might just leave it. So I'll just do like 1 minus the quantity x minus 1 squared. Oh, sorry, off the screen. Thank you. Okay. I might just leave it like that. Just subtract the entire quantity over rather than expanding it out and simplifying. I don't really know if it's going to be worthwhile to do it that way, so we'll just leave it. And then square root both sides, of course. And to get b equals the square root of 1 minus the quantity x plus 1 squared. Again, if you want to expand it out, you're welcome to, but I don't think it's going to help. Okay, and so there's the secant. Oh gosh, I need to zoom out, I guess. There we go. Oh, geez, I did. Thank you. Thank you. Yes, very good. Okay. Yes. Okay. So that's how you do that, right? And that would be the answer right there, okay? So it's very similar to ones that we did before with just numbers. Now you throw in some variables in there, but it's still the same idea. Use Pythagorean theorem to solve for that third side, and then just use your SOHCAHTOA or reciprocals to do that. Any questions on any of that? Pretty straightforward stuff. Hopefully you remember that somewhat. And again, I'll come around and help. We'll get you some practice on that here in class, and because I think that's really where you'll get it down better when you actually do it on your own. All right. Let's take a look at letter K. Letter K was a pretty big letter. Had a lot of stuff going on with it. Okay, letter K had a lot of stuff going on with it. Okay. So I feel like I should have just done this from the start, show you guys the answers rather than ask the questions. But there are my answers. Okay, so for again for K, you're at all the directions for K are just all solve for X, where X is a real number. Ignore the blue pen there. I don't know what that is, but anyway. So there's number 1. So you got -6 and +3, 2, plus or minus 1, plus or minus 1, 8, or 2. 3 is kind of interesting. You do it 2 different ways. You expand it out and then subtract the 9 over so that you're equal to 0 and then factor that quadratic. Or you could have square rooted both sides right off the bat and have x minus 5 equals plus or minus 3 and then separate that into 2 equations. One where x minus 5 equals positive 3, one where x minus 5 equals negative 3, and solve it that way. Either way results in the same solution there. Okay. Number 4, I couldn't get to factors, so we rely on the old faithful quadratic formula, which is something that you will need to know how to do for sure. Okay. Questions on 1 through 4? Can I scoot it up? Yes. All right, there's 5 and 6. For 6, I just added the 5 over the square root of x minus 1 to the other side, and then multiply both sides by the square root of x minus 1 to cancel out the denominator there. Just have 5, and that would be just an x minus 1, just x equals 6. And I also checked it too. Right? You have those square roots, you want to check for those extraneous solutions sometimes. And number 5 required the use of logarithms. like use your calculator and getting like a decimal answer here, that may be okay, but we also want to be comfortable with leaving, leaving our answers in like a simplified form, kind of thing, like this, or the natural log of 2, which is right down further, right? So the logic flow here is that ln 4 divided by 2 is the same thing as 1/2 times natural log of 4. And when you have a number in front of a logarithm, that can go up as the exponent, so it's natural log of 4 to the 1/2, which then simplifies to 2. Okay? So it's not 2 because 4 divided by 2 is 2, it's 2 because 4 to the 1/2 power is 4. That's why it becomes 2 in there. Questions on anything there? All right, flippy over. Again, 7, this is absolutely fine for your final answer there for x. Okay, in fact, it's a better answer because if you give me any sort of decimal answer, you're going to be rounding it, right? This is a precise answer right there. And that's the precise answer right there. Question, Willie?
Can you go over number 8?
Sure. So, fractions, right? Is that the problem? You're just like, how do I? Yeah. Okay. So, I'm sure you know you need a common denominator, right? Okay. And so it's a matter then of like, all right, how do we get that? Well, if you look at what we've got, actually, I'll just look at it right here. None of these denominators really have any common factors. So we kind of have to do the old method of every other denominator multiplies, to the numerator, stuff like that. So here the 4 is going to have to multiply by the 6 and the x plus 3. You see that? So then it's 4 times 6 times x plus 3. Got that? And then here for this number, it's got a 6, but it's missing the x minus 1 and x plus 3. So this 1 is going to get multiplied by x minus 1, x plus 3. Right? And then finally, the x plus 3 is in this denominator, but it's missing the x minus 1 and the 6. So we'll multiply that 5 by x minus 1 and 6. Okay? And really, I guess I'm kind of not doing an intermediate step here. So I guess technically what I'm really doing here is this. I don't want to like just do some math magic here and make people think that I'm not doing something I'm supposed to do. But of course, I multiplied 4 over x minus 1 by 1, right? But it was really 6 times x plus 3 over 6 times x plus 3 like that. And then, actually, no, that's not what I did. I guess I did because of the way I wrote it. I wrote it like this. Oh gosh, yeah. So 6 like that, and I kind of multiply, and then this whole thing by like. This is more what I kind of did here. I multiply both sides by 6 times x plus 3 times x minus 1. So when I did this one times this one, the x minus 1 would cancel, leading to 6 and the x plus 3 times the 4. And then here the 6's would cancel, leading to the x plus 3 and the x minus 1 times the 1. And here the x plus 3's cancel, and the 6 and the x minus 1 times the 5. That's what I really did there. But it's essentially, again, getting a common denominator. Here I'm what some teachers call clearing the denominator or whatever. But it's the same kind of principle. Okay? So this makes things a little bit nicer. You don't have to keep writing the denominator this way. It lets you avoid writing the denominator, basically. So, but anyway, and then from there, 24 times the 24, and then you distribute it. Here you want to be a little bit careful. You have that minus sign in front of this product. So this minus sign distributes to every term in here. Okay, so with a negative x squared, and then this is positive 2x, but then it's minus 2x, and then minus 3 becomes minus negative, so plus 3. That's something you want to be careful of right there, too. That minus sign will distribute all those terms. Okay. So then eventually you should get negative 15 and 7. It does factor. I didn't think it factored originally. I went to the quadratic formula. I was like, wait a minute. That does factor. So that just factored. Okay. Did that answer your question, Lily? Okay. And then trig equations. All right. 9, 10, 11, I don't see, let's see here. Well, 9 and 10, I don't see, well, I guess, yeah. 9 is pretty straightforward. You just have to isolate the sign. Sine of x equals -1 when at 3 pi over 2, but the answer is between 0 and 2 pi. 10, you have to factor out a tangent. And then that'll be 2 cosine x minus 1. Since it's equal to 0, you can set each factor equal to 0 and solve. So you get 0 pi, pi over 3, pi over 3. Number 11, you add the 1 and divide by 4, and then you square root both sides. You should end with a plus or minus 1/2 here, resulting in 4 solutions, right? Pi over 6, 5, pi over 6, 7, pi over 6, 7, pi over 6. So questions on 9, 10, or 11? Yeah. 10? Okay, so at what point, I guess? Where did I?
When 10x equals 0, and then cosine equals 1/2.
Okay, so from here to here? Or from here to here?
The
First one's from here to here. Right, so when you have two things that multiply, right, and they're equal to 0, that's a zero product property. It's the same principle we use when we factor a quadratic and we set each factor equal to 0. Same idea here. If two things multiply to make 0, and that means one of those two things has to equal 0. So I set the tangent of x equal to 0, and then I set 2 cosine x minus 1 equal to 0, and then quick mental math made it equal to 1/2 because it's just solving for it. Okay? That's it. Now, number 12 I want to talk about too. Okay, because number 12, we have this little 2 that shows up inside the tangent there, and that results in a period change, right? In fact, a period shrink. So tangent repeats, has a period of pi. It repeats every pi units, okay? And so when we solve tangent of 2x equals 1, you can solve it just like you're solving tangent of an angle equals 1. So, for example, the way I kind of think about it is this way. I'll kind of draw this over the side here. I think, okay, let's just say this is tangent of theta equals 1, okay? When does tangent of theta equal 1? Well, that's when theta is pi over 4 or 5 pi over 4. Okay, like that. But of course, we're not interested in, well, let me back up. Pi over 4 or 5 pi over 4, and we could add pi to those solutions to continue to get additional solutions, right, if we wanted to keep adding pi. But we don't have tangent of theta, we have tangent of 2x. So instead of theta, I replace that theta back with the 2x that I substituted in for originally. So I replace the 2x with theta, solve it for theta, and then replace the theta with 2x. Okay, pi over 4, pi over 4. Just continue solving for x, you divide by 2. Pi over 4 gets divided by 2, pi over 8. 5 pi over 4 divided by 2, 5 pi over 8. Right? The period of pi gets divided by 2, and so this thing repeats every pi over 2. Okay? Or in terms of 8s, 4 pi over 8. So pi over 8 and 5 pi over 8 are solutions, but we can add another 4 pi over 8 to this pi over 8, get 5 pi over 8. Add another 4 pi over 8 to this, get 9 pi over 8. That's still between 0 and 2 pi. And then add another 4 pi, get 13 pi over 8, and that's still between 0 and 2 pi. Adding one more 4 pi over 8 would result in 17 pi over 8, which is not between 0 and 2 pi. Okay? So you get two additional solutions there to that equation. Two additional solutions. Okay. So wanted to highlight that one. Questions on that at all? Okay. So just be careful with that, right? And tangent's different than sine and cosine, right? Sine and cosine, they repeat every 2 pi. Tangent repeats every pi. Okay, tangent repeats every pi. All right, last two here, and I'll get you guys started on your assignment. Okay, last two. Just solving for z. Get z by itself. Okay. And again, I skipped steps here, but there's at least a little bit of what's shown. Questions on any of those at all? Questions on any of those? All right. Well, if if there are no questions, then you guys can get started on your assignment here. That's all I've got to show you. All right, so again, tomorrow's quiz will not cover K. It only goes up through letter F. Okay, so A, B, C, D, E, F, right? That means no trig, right? F was like those mistakes. So you got lines, parallel, perpendicular, writing the equation of lines you got to think about. Okay, watching out for common mistakes and stuff like that too in that. Let's see here. Composition of functions and evaluating functions, including this little difference quotient here. You want to, like I said, that's important to calculus. May show up on the quiz tomorrow. May not, though. Simplifying expressions with fractions and stuff like that, too. Okay. Factoring, including that sum and difference of cubes that Mr. Widmeyer showed incorrectly. There it is. I fixed it in this paper, too. Okay. So make sure you got that down, especially because I showed it wrong at the very first, but hopefully it's now fixed in your brains at least. But I've shown it before, or shown the new one, the right one here now. And then this stuff, okay, simplifying those. Good. All right, so those are kind of your topics for the quiz tomorrow. Okay. In the meantime, you can check. Let's see here. I think I'll post this. I'll post the assignment here on the board. So it's in section 1.5. And it's going to be numbers 95 to 105, the odds. And then 117 to 135, the odds. Okay, so there's your assignment. And I'll post this to the classroom too. This will be homework if you don't finish it. Yep, that's the homework.